And they get handled largely the same way, which we'll see here in a second. So any moving object has momentum, just by definition. You guys probably have an existing understanding of the concept of momentum. Momentum depends on two things. The amount of momentum inside a moving object depends on two things. And they're largely determined by how scary the object would be to stop. So it's similar to the concept of inertia. And I think the example I gave to you when we were talking about inertia on the very first day was my son running at you, he's 2, versus me running at you. I'm 36, and he's 30 pounds, and I'm not 30 pounds. Which of the two of us is more irritating to stop? Or more difficult to stop, or more scarier to stop? It depends on two things. What does it depend on? If I tasked you with stopping an object, what two things would you consider to decide whether or not it's a good idea to stop that object? You bet. Is that what you were going to say here today? Mass and, I don't want to use the word speed, we're going to use the word velocity. And I mean, and you can think of it as how scary is the object to bring to a stop. They'll give you a pretty good idea of your understanding of the momentum of the thing. My son is walking at you. He's light. He's slow. You could stop him with a hand on the forehead. It's not a big deal. If I'm walking at you at the same speed, also probably not a big deal, but you're going to have an understanding that stopping me is going to be a little bit harder than stopping him. If he's running at you and I'm walking at you, now there's things to consider. He moves, when he wants to move quick, he can move real quick. And so if he hits you hard enough, he can knock you down. Something to consider. But if I'm moving at the same speed my son is, now you've got a bigger deal. My mass is that much greater than my son's. For our velocity the same, it's going to be an issue. Same idea, we can take it down to really, really small objects. I have an eraser. I toss the eraser to Vian, not a big deal. You guys borrow erasers from me all the time. If I put the eraser inside of my air cannon over there, because I have one of those, and I point it at Vian, Vian will be a little bit more concerned. The mass on this thing is small, but the velocity is great. And this is the concept behind something as simple as going hunting. Bows and arrows, guns and bullets, it's not like those things explode, but you propel a small object at an incredible rate, and now you've got a problem. You've got something you've got to deal with. Well, whatever is on the receiving end of this object now has a problem. I could throw tiny bullets at you all day, and it's not a problem. I put the thing in, we go to the gun range, and now all of a sudden there's something to respect. So the idea here is that mass and velocity and the concept of how scary something is to stop is a pretty good understanding of momentum. And that is it for the formula. Momentum is equal to, the P is what we use for momentum, because M is mass. P for momentum, and it looks like P, it's not actually a P, but for all intents and purposes, it's a P. P is equal to the mass of the object times its velocity. You multiply those two things together, and conceptually, that value you get is the quantity of momentum possessed by an object. It's abstract. It's not like, I don't even know what I was going to say. It is, yeah, it's entirely abstract. It's not like mass where you can step on a scale and like, oh yes, this is my mass everywhere in the universe. Momentum is an abstract concept. It gives a relative idea of how difficult these things are to deal with. It looks like a P. We'll treat it like a P. It's not a P. It's the Greek letter P, which is called rho. For those of you who know your Greek alphabet. It's a Greek letter. Represents momentum. Why it's rho, I do not know. M is mass, exactly as you'd expect it to be. Mass always gets measured in kilograms. Velocity is V, measured in meters per second. That was the one thing we didn't talk about in the truck up the incline. Once you find the acceleration will be in meters per second squared. The velocity was 150, so you need to convert that, but that's easy for you guys to do. So momentum is a vector. Momentum is a vector because it depends on a scalar and a vector being multiplied together to give us this value. So because momentum is a vector, it has both a direction and a magnitude. And the units are determined largely by, well, exclusively by how this thing is constructed. Momentum is equal to the mass times the velocity. The mass is measured in kilograms. The velocity is measured in meters per second. So the units for momentum are kilogram meters per second. It doesn't get a fancy unit like force did. When we first talked about force was equal to a mass times an acceleration. So we said that, well, mass times acceleration is kilogram meter per second squared. Or we also just call it a Newton. But if you take a look at what a kilogram meter per second is, I'm going to go up here for a second. If I have my kilogram meter per second, and we had for force, the one I just gave you, so I just talked about, was kilogram meter per second squared. That's a mass times an acceleration, just like a force is. What could I do to this thing to make it look like this thing? What could I multiply a kilogram meter per second squared by to get a kilogram meter per second? Well, if I square root the whole thing, then I got a root kilogram times a root meter times a sec, or divided by a second. I don't want to do that. I just want to get rid of the seconds squared. I just want seconds. If I multiply by meters, then I'm going to get meters squared up here. But I can't square root just part of the thing. I have to square root the whole thing. There's a really easy way to get rid of that squared. Here, Day. Nope, that's not a squared means you're multiplying. Seconds squared means this is seconds times seconds in the denominator here. To get rid of it, we're just going to multiply by seconds. Because multiplying a fraction by a whole is, I take this thing, I put it over 1. What I'm going to get here is a kilogram meter second over seconds squared. And then these are going to cancel. I get a second divided by seconds times, second divided by seconds times seconds. One of those seconds is going to cancel. And now I've got, all I did was I took my force. This guy here is force. I multiplied it by a time, lowercase t, and I get a kilogram meter per second, which is the same unit we have here. So momentum is not just equal to m times v. Momentum is also going to be equal to force times time, because the units are equivalent. Forces are, so momentum is also equal to a force times a time. And forces are measured in newtons. Times are measured in seconds. So the units of momentum, you can either write them as a kilogram meter per second, or equivalently, you could write it as a Newton second. So now we've got two expressions for calculating the momentum of an object. The momentum of an object is equal to how massive it is times how fast it's going, or the force being applied to an object times the time the force is being applied will give that object a particular momentum. stop me at any point if you have questions. But let's take a look here. So, first two. We want to calculate the momentum of a 92-ton train traveling at 80 kilometers per hour. That would be terrifying to stop, so presumably the momentum of this thing is going to be really large. The mass of this thing is 92 tons. We're in Canada, so what's a ton worth? 1,000 kilos. So 1 ton equals 1,000 kilograms. A ton is different depending on where you are in the world. I want to make sure we clarify that. So if we've got a 92-ton train in Canada, that's going to be 92,000 kilogram train. Not a very big train, all things considered. Well, not big for a train. And the velocity is 80 kilometers per hour. Now, mass is in kilograms. We need velocities in meters per second. So to take kilometers per hour and convert it to a meter per second, we're gonna, you bet, we're gonna divide this thing by 3.6, and that's gonna give us a value in meters per second. 80 divided by 3.6 is 22.2 repeating meters per second. So then to find the momentum of these things, or of this thing, momentum is equal to mass times velocity. The mass is 92,000. The velocity is 22.2 repeating. And the value we get for the momentum of this thing is 2,044,444 kilogram meters per second. That is a large value. Don't try and stop the train. Okay. The calculations here are simple. So let's make it conceptually more interesting. A baseball of mass 0.14 kilograms, so 140 grams, is moving at 35 meters per second. So that's just over 100 kilometers per hour. As far as baseballs can be thrown, that's not very fast. A fast pitch would be like 100 miles an hour in baseball. So this is 100 kilometers per hour, which 100 miles is 160 kilometers per hour. The ball is moving quick, but not as fast as it could. Let's find the momentum of the ball. Well, the momentum of the ball, momentum equals mass times the velocity. The mass is 0.14. The velocity is 35. The units are good. We just multiply them together. The momentum of that ball is 4.9 kilogram meters per second. I mean, someone throwing a ball at you at 100 kilometers per hour, perhaps you're not going to be comfortable stopping that thing. But do I have any baseball players in here? Nobody plays baseball in here? That's a lost art. Do any of you have Mr. Kidd as a teacher? Yeah. Mr. Kidd and I used to be on beer league baseball team together. And a baseball moving at you at 100 kilometers per hour or 35 meters per second, that might be a line drive. Anyone in the infield who's volunteering to play baseball would be reasonably expected to stop that thing. You have your equipment, you can put it up your glove, you catch the thing. For a person who's played baseball, this is not a big deal. That's a relatively small value. I would way rather stand in front of that baseball than this train, for example. But just to give you an idea of equivalent momentums, let's find the velocity at which a bowling ball, 7.6 kilogram object, which is a small bowling ball. Actually, that's a moderate-sized bowling ball. 15-pound bowling ball, 18-pound bowling ball. How fast would this thing have to go to have the same momentum as this baseball, moving at 35 meters per second? Well, let's do it. The momentum of an object is equal to its mass times its velocity. We want to figure out how fast the bowling ball would go to have an equivalent momentum. So we'll take this 4.9, and this is going to be the momentum we want the bowling ball to have. So this is going to be 4.9 equals, the mass of the bowling ball is 7.6 times v. We want to figure out how fast the bowling ball would have to go. Solving this thing for v, we're going to get that v equals 4.9 divided by 7.6. Divide 7.6 on both sides. And you get the velocity of the bowling ball would be 0.64 meters per second. So let's see if I can demonstrate 0.64 meters per second for a bowling ball. This is how fast the bowling ball would have to go. To have an equivalent momentum for a baseball being pitched at you at 100 kilometers per hour. This is not an intimidating bowling ball to stop until you take into account that the thing weighs 20 pounds. Then, I mean, and this is where things get interesting when you're dealing with momentum out in the real world. It's the same concept we talked about with inertia. We always look at the slow move or the fast moving light objects and be like, yeah, that's scary. But rarely do we step in and think about the slow moving massive objects. A 20-pound bowling ball rolling at you that fast isn't a lot, but anyone who interacts with that it's going to be more than you expect to slow that thing down. It's the same thing with the example I gave you when we were talking about inertia. There's always the hero that tries to stop the rolling car. The car's not rolling very fast. Oh yeah, I can catch the thing. Anyone who's in auto should know if the car is rolling, do not get behind it. Even if it's rolling slow. A car is a massive object. Even moving slow, it's got a lot of momentum. The bowling ball doesn't have to move very fast to be equivalent to the baseball moving at 100 kilometers per hour. If the baseball moving at 100 kilometers per hour causes you any level of concern, so should a slow-moving bowling ball. Momentums are equivalent in this case. Questions, comments, concerns? Okay. Let's do one more thing. Momentum as just a raw value is not nearly as interesting as what would it take to change the momentum of an object, and answering those kinds of questions. So we're going to do two examples where we look at changing the momentum of an object and what it takes to do that. So first we're going to look at what change represents. How do I calculate change? We used a Greek letter for this before. What was the Greek letter we used to represent the change in a value? Delta, the Greek letter triangle. And if I wanted to calculate the change in something, I would use delta in front of that concept. So in this case, we want to figure out the change in momentum. What we're going to look at is delta momentum. Delta represented a method to calculate change in things. What was the method? If you decide today you're going to take advantage of a Black Friday deal and get a gym membership at a reduced price, you're going to start to go to the gym, whether to lose muscle or gain weight or whatever it is you decide to do at the gym. It's actually backwards. Whatever you decide to do at the gym, how do you measure your progress? Whatever your goal is, how do you measure progress? At the gym. You take pictures, sure. And then how do you what about the pictures are you comparing? Yeah, can you give me Yek or Navin? Okay, how are you comparing those? What are you comparing? Before and after. You look at the after picture, you look at the before picture, or your stats, the weight, however much you weigh or however much you can bench. You say, now I can do this. Before I did this, have I made any progress? This is conceptually equivalent. Change in something means you're looking at where you are now or finally, and you're comparing it to or subtracting away whatever value you started at. The change in something is always the final minus the initial. If I told you I spent 6 months at the gym and I can bench 200 kilograms, is that impressive? Well, if I told you 6 months ago I could bench 199, and now 6 months later I can bench 200, those gains are not impressive. It doesn't matter what you can do at the end. It doesn't matter what you did at the beginning. What matters is the relative difference between the two things. So that is the concept we use here for change. Let's look at change in momentum. So change in momentum means that when we calculate this side, if momentum is changing, one of these two values is changing. Which one makes sense to change? Velocity. Mass is probably not going to spontaneously change for most of the objects that we look at. So when we look at change in momentum is going to equal whatever the mass is. This is going to, for what we do, this is going to remain constant. There are other objects where this would not remain constant, and then things get complicated. Things like rockets. Anything that has propulsion with fuel that gets consumed. If you're looking at the momentum of a rocket, yes, the velocity is increasing, but the mass is decreasing, for example. So that gets more complicated. In this one, we've got a 50 kilogram water balloon being thrown against a wall. It comes to a stop. It doesn't explode. That's a whole other issue. It comes to a stop. So the mass has remained constant. What we're looking at now is a change in velocity for these objects. At this level, if the momentum is changing, it's a change in velocity. So let's take a look at what we've got. I'll draw the thing. Here's our wall. And here's the water balloon. It's moving this way. It has an initial velocity of 32 meters per second. How someone got a water balloon to move at 32 meters per second is beyond me. That's a over 100 kilometer per hour water balloon. And the thing is coming to a stop. So finally, VF is going to be what? Zero. How the thing doesn't break on impact, I don't know either. It doesn't matter. What's the change in momentum? Well, change in momentum is equal to the final momentum minus the initial momentum. So that's going to be, the mass doesn't change. That'll be the mass times the velocity at the end minus the mass times the velocity at the beginning. So delta P, or delta change in momentum, is going to equal 0.5 times 32. Nope. 0.5. Finally, it's 0. 0.5 times 0 minus 0.5 times 32. We're going to get a change in momentum here of negative 16 kilogram meters per second. So an impressive change in momentum. Part B says, I'm going to take that same object, well, the same mass object, so now it's a bouncy ball. We're going to throw it at the same rate, and it's going to come back at you at the same speed. How does its change in momentum compare to that of the water balloon? What does your intuition say? Throwing an object and having it stop at a wall, or throwing an object and having it come back at you? Which one of those is going to have the larger change in momentum, does your gut tell you? Presumably the one that comes back. I would be more concerned about the coming back object. So let's take a look at that. Let's just run the math. We're going to draw a picture to make it really clear what's going on here. I've got a bouncy ball coming into the wall with an initial velocity of 32 meters per second. It's going to make impact with the wall, and now the thing is coming back with a final velocity of 32 meters per second. This object is now moving in two different directions. So I have to call one of those objects, I have to label those objects, or the directions rather. As soon as we've got an object moving in multiple directions, I need to talk about positives and negatives. Which way do you want to call positive? Towards the wall or away from the wall? Away from the wall? Okay. So that's the direction we're calling positive. Oh, and in this case, which was the direction I assumed was positive? Just so we're clear. So, yeah, towards the wall I called positive. Because this velocity when I plugged it in was positive. Here, so now we're going the other way. Change in momentum is going to be momentum final minus momentum initial. So that's going to equal the mass times the velocity final minus the mass times the velocity initially. And we said, you guys said, that away from the wall is positive, which means your final velocity, 32, is going to be positive, and your initial velocity, 32, is going to be negative. Because it's going towards the wall, you said away from the wall is positive. So, what we're going to get here is 0.5 times positive 32 minus 0.5 times negative 32. We've got a double negative in here, which is where these momentum questions always snag students. So half times 32 is going to be 16. Negative half, times negative 32 is going to be positive 16. The change in momentum is positive, which means the change in momentum is in the direction, the ball's moving at the end, which makes sense. And it's twice as big as it was. So for an object that's rebounding, your change in momentum is going to be bigger than if you just brought it to a stop. That's it. This is the intro to momentum. We're going to do two lessons next week. Yes. 2 lessons next week on momentum. So Monday, Tuesday. Your test is still going to be on Thursday. Wednesday is the day I will give you is the one day I'll have for review in class. But now you've all got the review packages. You can start reviewing it over the weekend. You could stick around for a tutorial. Tutorial starts in 20 minutes. And start working through that review now if you'd like. Just so you know what the upcoming days are going to look like. Monday, Tuesday, we're going to do impulse and then collisions and explosions. And then Wednesday is going to be review. Thursday's your guys' chapter test. This is the intro to momentum. I'm done. Here's what I want you to look at. There's 20 minutes left in the block. Or maybe 13 minutes left in the block. There's 10 questions here, and I want you to do all of them. They should not take you long to do. On your market set giver.